I'm really happy to hear you. I'm really happy that you have a chance to give this mini course of lectures, because it is really very important for many from Russia and from China and actually from other countries to know some ideas and some methods you can share with us dealing with Cayley graphs and digraphs and automorphism of Cayley graphs. So that is amazing that you have this chance to share your knowledge with us. Thank you very much. And let me just give a very brief introduction. So Joy Morris completed her PhD in Canada at Simon Fraser University. And since that time, as far as I understood, she is now a professor at the University of Lethbridge in Alberta, Canada. And the main research area is algebraic graph theory. And now we will listen the first talk of the mini course named as Topics in Automorphism of Cayley graphs. And today I hope that we can see some new methods on Cayley graphs and digraphs, and especially in circulant graphs, right?
Yeah, thanks a lot for that kind introduction.
Yes, thank you so much.
So yes, I'm going to give a fairly gentle introduction today about Cayley graphs in general and circulant graphs and what they are, and then get more into the technical aspects of what I want to cover in the next 2 lectures. But first, I wanted to begin by explaining to you where. I apologize for that. I'm not sure what just happened. I lost my.
You see, sometimes it's happened. Please don't worry. Just to continue. Yeah.
Okay. Lost my connection. Fortunately, I have my other connection, which told me that I'd lost my connection. So a graph gamma is vertex transitive if it's automorphism group. And this is the collection of all bijections on the vertex set. That preserve edges and non-edges. So if it's automorphism group, acts transitively on the set of vertices. In other words, if for any 2 vertices, V and W, in the vertex set, there is some element in the automorphism group of my graph gamma such that it maps V to W. So from that, we can now define a Cayley digraph. If we start with any group G and any subset S of the elements of G, then we define the Cayley digraph on G with the connection set S to have the vertex set be exactly the elements of the group G, and the edge set gets defined by G. An element G of our group is adjacent to an element little sg if and only if little s is an element of our connection set. So in general, what I've defined here will give us a digraph. It may give us loops. And so more specifically, when I want a graph, then I need to have S, this connection set, be enclosed under inversion. And I'll explain that in a moment on my next slide. And the second point that I want to make is this may have loops. It will have loops if and only if I allow the identity element to be in my connection set. So if the identity element is an element of the connection set, then there will be loops at every vertex. And when all I really care about for my purposes are the automorphisms of the graph, whether or not you have loops at every vertex does not affect what automorphisms there are. So you can allow the identity to be in the connection set or not. It doesn't make a difference for my purposes. But if I want a graph rather than a digraph, then I will need the connection set to be closed under taking inverses. So again, I said we get an arc from G to SG exactly when S is an element of the connection set. And if we want to have a graph rather than a digraph, then we want to have an arc coming back in the opposite direction. Whenever we have an arc going from G to SG, we want an arc also going from SG back to G. But that, by our definition of the edges or the arcs in this graph, will happen exactly when S inverse is in S, because G is S inverse SG. So left multiplying by an element of the connection set gives me an arc. So an example, a Cayley graph on the cyclic group of order 12 with the connection set 2, 5, and 7. This is not closed under inversion. So 2 is in there, but 10 is not. 5 and 7, however, are inverses of each other. So this has some arcs and some edges in this graph, and it ends up looking like this. And so, yeah, so I've drawn on the edges of length 5, I've drawn arrows in both directions. These small arrows in here end up going on both directions in each edge, and I replace that with just an edge typically. But the elements that come from the connection set, from the element 2 of the connection set, all go sort of clockwise around this circle. So this is this particular Cayley digraph as an example of what I'm talking about. If we're working with a non-abelian group, like the dihedral group of order 10, and say rho is a rotation. So in this case, I'm having rho to the 5th is the identity, and tau is a reflection. Tau squared is the identity. In this case, the order of the action becomes important, and it is important that we're multiplying on the left rather than the right to get our edges. So when I write out all of the elements of our group to create my vertices, and then I can create edges that come from rho tau. Rho tau is an element of order 2. So its inverse is rho tau, which is then in the connection set. So that gives me these edges in the graph. And then also I get some arcs in the graph from the element rho, and the arcs are going to look like, well, they go from rho to the 0 to rho to the 1 to rho squared to rho cubed to rho to the 4th, back to rho to the 0. And in the other, on the other half, because tau inverts rho, they go this way, because when I multiply, for example, tau rho to the 0, when I multiply that by rho on the left, I get rho tau rho to the 0, which is just rho tau, but that is tau rho inverse, which is tau rho to the 4th. So I get an arc going from tau rho to the 0 to tau rho to the 4th, and so on. All right, I'm going to leave a number of exercises in my talk, things that I think are relatively easy to prove from the definitions I'm giving, but I'm not going to go into the proofs of them. So I will give an idea for the proof of at least some of them. At this point, it should be an exercise to show that the Cayley graph G on G with the connection set S will be connected if and only if the connection set S actually generates the group G. And this is because if the connection set S generates the group G, then we can get using a word in S to any vertex or element of G. And the converse is similarly true. And similarly, it's not too hard to prove. In fact, this is true for a much broader class of graphs than just Cayley graphs. A Cayley graph is strongly connected if and only if it is weakly connected. This is, in fact, true whenever we have a this should be a digraph. This is in fact true for any digraph that is regular. It will be strongly connected if and only if it is weakly connected, if it has the same number of in at arcs as out arcs at every vertex, which is certainly going to be true for a Cayley digraph. Strongly connected means there is a directed path between any two vertices, and weakly connected means that the underlying graph is connected. So for Cayley digraphs, there is no difference between strongly connected and weakly connected. And in fact, more generally, that's true for vertex transitive digraphs. And as I said, even for regular digraphs. So now let me define a circulant graph, which is a particular type of Cayley graph. And it's what my first example came from. A circulant graph is a Cayley graph on a cyclic group. And when a group is abelian, we often, of course, use additive notation rather than multiplicative notation to denote, to explain what the group is doing. And I have already followed that, that convention in that first example that I used. So a permutation group acting on a set is said to be regular if for any two elements of the connections, of the set omega on which the group is acting, there is a unique element of the group that maps one to the other. So a regular action has to be transitive. We've already seen transitive action, but it's sharply transitive. We have a unique element taking any element of the set to any other element of the set. And something that I certainly teach in a first course on group theory, and I think many of us do, is that every group does have a right regular action on itself, or a left regular action, in any case, a regular action on itself. By multiplication on the right or left. In this case, I'm assuming the right. So we define this action for any two elements in our group. If I want to know where G takes H to, it takes H to the element H right multiplied by G. And again, in introductory courses on group theory, we use this to prove that every group is a group of permutations. Of the so it's a subgroup of the symmetric group acting on the elements of itself. Okay, so this is important because when we're talking about Cayley graphs, we always have that this right regular representation of an element of the group. So this action by right multiplication is an automorphism of the Cayley graph. So to show this, let's take any two elements of our group. So these are vertices of our graph. And I want to know if when their images are adjacent, I would like to show that they have to be adjacent. So their images, I'm assuming their images are adjacent. Well, that's true if and only if by the definition of a Cayley graph, there has to be some element S in the connection set such that the image of V is S left multiplied by the image of W. But now I'm going to use the definition of what GR does. The image of V under GR is VG, and the image of W under GR is WG. And since G is a group, little g has an inverse, so I can cancel the G's, and I get V is SW. And that means that V is adjacent to W. So their images are adjacent if and only if the vertices were adjacent in the first place. So right multiplying does give us an automorphism of the graph. And that means that the right regular representation is sitting inside the automorphism group of the Cayley graph for every subset S of G. So this is true for Cayley graphs or digraphs. We always have this regular subgroup of automorphism groups. This was first observed by Savadusi a long time ago, back in the 60s or 50s, maybe even. And it's a very useful characterization of Cayley graphs. So in particular, this means that every Cayley graph is vertex transitive because it has this regular subgroup of automorphisms, and this subgroup is regular, and therefore, in particular, it's transitive on the vertices. So if I'm trying to find, if I have an X and a Y, two vertices in my graph, and I want to know what particular element maps X to Y, it's not hard. I take X inverse Y, the right regular representation of that element. That right multiplies X by X inverse Y, which gives me Y. And X inverse Y is the only element of the group. That when I right multiply X by this, I get Y. So this action really is regular on the vertices of my graph. So every Cayley graph is vertex transitive. The converse of this is not true. Not every vertex transitive graph is Cayley. So I can define the Peterson graph, for example, here as a Kneser graph. So we define it as a set, a collection. So the vertices are subsets of order of size 2 from 1, 2, 3, 4, 5. So for example, I can make this 1, 2, and we make 2 subsets adjacent if and only if their intersection is empty. So 1, 2 will be adjacent to 3, 4, and also to 3, 5, and also to 4, 5. And 3, 4 is also adjacent to 2, 5, and to 1, 5. And 4, 5 is also adjacent to 2, 3, and to 1, 3. And the only vertex that's adjacent to 1, 3, 1, 5, and 3, 5 is 2, 4. And the only thing that's adjacent to 2, 3, 2, 5, and 3, 5 is 1, 4. So with this labeling of the vertices, well, with this labeling of 10 points by all of the subsets of size 2 from 1, 2, 3, 4, 5, if I define adjacency by two sets being adjacent if and only if their intersection is empty, I get exactly the Peterson graph. And because this definition of adjacency depends on something that is preserved by any element of the symmetric group, this means that the automorphism group of the Peterson graph actually contains the symmetric group on 5 points. And in fact, it turns out to be equal to the symmetric group on 5 points. Which is a group of order 120. It acts vertex transitively. A regular, if there were going to be a regular subgroup, if this were going to be a Cayley graph, it would have to have a regular subgroup of automorphisms sitting inside this. And that regular subgroup would have to have order 10, because that's how many vertices there are in the graph. There are only two kinds of groups up to automorphism that have order 10. There are cyclic groups or dihedral groups. And there is no regular subgroup of the natural action of the symmetric group of order 5 on these 10 points that has order, that there's no regular cyclic subgroup of order 10, and there is no dihedral subgroup of order 10 either. Okay, that acts regularly. That's what I just said. The symmetric group acts vertex transitively. A regular action would have to have order 10, would have to therefore be cyclic or dihedral, and there is no such action. So another exercise that you should be able to figure out based on the definitions and what I've explained so far is that, as I said, a digraph or a graph is a Cayley digraph or graph on a group if and only if the automorphism group of the graph contains a regular subgroup isomorphic to the graph. So I've shown one direction of that very explicitly. I've shown that if you have a Cayley graph, we do have this regular subgroup of automorphisms, but you can also prove conversely that if you have a regular group of automorphisms acting on the graph, that graph is isomorphic to a Cayley graph on the group G. But the regular subgroup is not always the entire automorphism group of the graph. So for example, a circulant graph in this case is important, not directed graph, always admits reflections as well as rotations. So if I have a circulant graph, then we always have the regular subgroup of automorphism consists of rotations, adding I mod n to every vertex. That's what the regular subgroup does. Any element of the regular subgroup adds I to each vertex for some I. But in the case of a circulant graph, not digraph, we also have these reflection automorphisms that, say, for example, reflect through that line. That is also going to be an automorphism of this graph, but it is not one of those part of that regular subgroup of automorphisms. And this is a special case of a very general kind of automorphism that can arise in Cayley graphs. So when we have an abelian group, let me specifically consider abelian groups first, but this is true in greater generality, and I will state that on the next slide. But when we have an abelian group, if we define the automorphism iota of that abelian group to be the automorphism that inverts every element of the group, then if we have a connection set that happens to be closed under inversion, that then iota is in fact an automorphism of the Cayley graph. So let me prove this. Suppose we have two elements of our group, which are therefore vertices of the graph, G and H, and they happen to be adjacent. Well, that means that there is some element little s in my connection set such that G is little s times H. And now I'm going to let iota act on each of these vertices. G to the iota is G inverse, which is SH inverse, which is H inverse S inverse. But remember, this group is abelian, so this is S inverse H inverse. And H inverse is the image of H under iota. So now I have that I can write G, the image of G under iota, as the image of H under iota left multiplied by the inverse of S. But because this connection set S was closed under inversion, and little s was an element of S, that means S inverse is also in the connection set. And therefore, this means that the image of G under iota is adjacent to the image of H under iota. So I've just shown that iota is an automorphism group of this Cayley graph, or digraph if it's a digraph. Sorry, no, Cayley graph. I'm assuming that S is closed under inversion, so this is a Cayley graph. And in fact, as I said, this idea is true in more generality, so I just picked this automorphism iota that happened to invert every element in an abelian group. That's always an automorphism of any abelian group. But whenever I have a group, and I happen to have a group automorphism that fixes the connection set that I've chosen. So in the case of iota, I knew that S to the iota was S inverse, but that was equal to S. In this more general situation, if I just happen to have that S to the alpha is equal to S, then that turns out to force the fact that alpha is an automorphism group, is an automorphism of our Cayley graph, or induces an automorphism of our Cayley graph just in exactly the way that iota did. All right. I seem to have gotten through those slides more quickly than I'd anticipated, but that is all that I wanted to present today. And then I will carry on with more about automorphisms of Cayley graphs and circulant graphs in particular in my next lecture.
Okay, thank you so much. Yeah, are there any questions to Joy? Well, not yet. Well, but you gave us some exercises, so who knows, maybe for the next lecture there will be some questions to you. Okay, thank you so much.
All right, thank you. Yeah, so in this lecture, I tried to explain some automorphisms that Cayley graphs always have, and circulant graphs in particular always have. And in the next lecture, I'll talk more about other how we can find out all of the automorphisms that a circulant graph has.
Yeah, right. Yeah, you're right. Yeah, it is very important. Yeah, so you gave the main statements we need to use in future lectures, right? Yeah.
Yes.
So it is very important. Yeah, right. Yeah. Okay, thank you so much. So we finished for today, and our next lecture will be in 2 weeks, actually on October 23rd. Okay, see you. See you.
Thank you.
Thank you. Bye.